So let's study the concept of convolution of two functions. So suppose that we take two functions ft and gt defined for our functions defined for t greater than or equal to 0. So this is in fact a definition for the convolution. Then the convolution, which is denoted by f star g at t, is defined as, is given by this formula. F star g at t is by definition the integral from 0 to t fu g t minus u du. So this integral from 0 to t, integral 0 to t fu g t minus u du may exist as a Riemann integral, as an ordinary Riemann integral, say when both f and g are piecewise continuous on 0 infinity, because then this function fu g t minus u will be piecewise continuous on 0 to t, and so this integral will exist as an ordinary Riemann integral. It may also exist as an improper Riemann integral, say when either f or g, or either f or g has a vertical asymptote at 0, at t equal to 0. So this means that it may exist as an ordinary Riemann integral, or it might exist as an improper Riemann integral, but in most cases that we will consider, both f and g will be piecewise continuous on the whole interval 0 to infinity, so it's going to be mostly ordinary Riemann integral. So let's see how it is important in the topic of Laplace transforms. So the problem, I can state a problem, is that given fs, which is the Laplace transform of a piecewise continuous function ft, and gs, Laplace transform of a piecewise continuous function gt, so f and g are piecewise continuous on 0 infinity, then compute the inverse Laplace transform of fs gs. So we can multiply these two functions fs and gs, and the question is, what is the inverse Laplace transform of the product fs and gs? So this answer is given by the convolution theorem. So as you might have guessed from the name of this theorem, the answer is simply the convolution of f and g, small f and small g. So it says that given ft and gt, piecewise continuous functions of exponential order alpha on 0 infinity, then if fs is the Laplace transform of ft, gs is the Laplace transform of gt, then the Laplace transform of f star g t is equal to Fs times Gs, or in other words, the inverse Laplace transform of Fs multiplied by Gs is simply F star G of t, which is defined for t greater than or equal to 0. Now here another remark is that if f and g are piecewise continuous functions of exponential order alpha, then f star g t is also piecewise continuous and of exponential order alpha, same order alpha. So if Laplace transform of f and g exists, in particular when they are piecewise continuous and of exponential order alpha, then the Laplace transform of the convolution of these two functions also exists, because then it is also a piecewise continuous function and it is also of exponential order. And the Laplace transform is precisely the multiplication of the Laplace transforms of f and g. So let's see some examples. So the first example, let's take an easy one. So let's take ft to be ft to be t and gt also to be t. So by the convolution theorem, we should have the inverse Laplace transform of 1 over s to the power 4. So note that the Laplace transform of ft is equal to the Laplace transform of gt. This is equal to 1 over s squared. So the Laplace inverse of 1 over s to the power 4 should be equal to the convolution of f and g. But we know what 1 over s to the power 4 gives us when you take the Laplace inverse, and this is precisely t cube over 3 factorial, right? So one has to check that t cube over 3 factorial is precisely, this is t star t, well, the function t star t evaluated at t. So both functions are t. So let's try to compute what will be our f star g evaluated at t. This is equal to the integral from 0 to t fu g t minus u du, right? So this is equal to 0 to t, fu is u and g of t minus u is simply t minus u du. So we get easy integrals to compute. So first integral, so there are two integrals here. The first integral is t times 0 to t u du, and then the second integral is 0 to t u square du. So the first term becomes t cube over 2 and the second term becomes t cube over 3. So if you evaluate this 2, then you get t cube over 6, which is t cube over 3 factorial. So it's just to check that this convolution theorem gives us the right results for when we take specific example, an easy example such as ft and gt equal to t. Now let's look at another example. So suppose that I want to take the Laplace inverse of two functions fs gs, where fs equals gs equals 1 over s square plus theta square for s greater than 0. So I forgot to mention one thing, which is that this Laplace transform for the convolution holds for all s greater than alpha, where s is the alpha is the exponential order for the functions f, small f and small g. So the convolution also holds for s greater than alpha. So let's go back to our proof for our example. So we have to compute the inverse Laplace transform of 1 over s square plus theta square whole square, 1 over s square plus theta square whole square. So now we know already that the inverse Laplace transform of fs times gs is simply the convolution of f star g of t, where ft is the inverse Laplace transform of fs, and the inverse Laplace transform of 1 over s square plus theta square is simply sine of theta t over theta. And similarly for gs, so gt is also sine of theta t over theta. So the convolution of these two functions we have to compute. So this is equal to 1 over theta squared 0 to t sine of theta u. So this is the first function fu, and the second function is the same, but we have to take theta of t minus u du. So this is the convolution of the two sine functions, s sine theta t star sine theta t. So evaluated at t. Okay. So we can explicitly compute this integral. Let's do this. So first step should be, we have to employ the formula for sine a minus b, which is sine a cos b. So sine theta cos theta u. So this is our theta, a equal to theta t and b equal to theta u, and sine of a minus b is sine a cos b minus cos a sine b, right, du. So let's compute what we get when we evaluate these integrals. So there are again two integrals here. So the first one is sine theta t, integral 0 to t sine theta u cos theta u du, and the second integral is cos theta t 0 to t sine theta u whole squared du. So we have to compute these two integrals. This is 1 and this is 2. So let's call it I1 and this is I2. So if you compute I1, this is equal to 0 to t sine theta u cos theta u du. So this is the easier of the two integrals, because we can just substitute v equals sine theta u, so that dv equals theta cos theta u du. So by changing this variable, so now v goes from 0 to sine theta t, and so we get the integral 0 to sine theta t of v dv over theta. So this is 1 over theta v square over 2 0 to sine theta t, and this is simply 1 over theta sine theta t whole squared over 2. So we have computed I1. So now let's compute I2. This is 0 to t sine of theta u whole squared du. Now again we can employ some basic trigonometric identities. So this is, I am writing it as 1 minus cos theta u squared, and then I can rewrite cos squared of theta u as half 1 plus cos 2 theta u du. So then we get the first integral here is simply t, then you have minus half, again you will get t, and the third integral is minus 0 to t cos of 2 theta u du, and this is nothing but sine of 2 theta u over 2 theta t over 2 theta. So therefore in the end we get t by 2 minus sine of 2 theta t over 2 theta. We can again simplify a little bit using the formula for sine 2 theta, which is 2 sine theta t cos theta t over 2 theta. Maybe I missed a 2 somewhere. Yeah, so there is a half sign here, so there is a half sign here, and so there is a half sign here, and one of the 2's cancel out, so this is 1 by 2 t minus sine theta t cos theta t over theta. So this is our I2. So we had sine theta t I1 minus cos theta t I2. So let's compute what it is. So then the inverse Laplace transform of FSGS is given by 1 over theta square sine theta t I1 minus cos theta t I2, and I1 was simply sine theta t whole square over 2 theta, or simply 2 maybe, 2 theta, and we had cos theta t by 2 t minus sine theta t cos theta t over theta. So now we can compute further, and you will get, if you take sine theta t over 2 theta common, then one factor comes from here, the other factor comes from here, but there is a cos theta t by 2 sine outside, so 2 theta will also come outside, and you get there is a plus cos square theta here, and you have sine theta square theta t square plus cos theta t square, and the next one is cos theta t by 2 times t. So this is just 1, and you get 1 over theta square sine theta t by 2 theta minus half cos t cos theta t. Now remember that we have this, our initial inverse Laplace transform function was 1 over s square plus theta square whole square. So there are other ways to compute it. For example, if you take the differential of 1 over s square plus theta square, and then you take 1 over 2s. So you know that what happens when you take a differential, and you also know how to compute the division by s for the Laplace transform. When you take the division by s on the right hand side, on the left hand side you will get integral. So you can also compute it by other means, and so we can check as an exercise. Check this result via other methods. So this is an exercise. Now as an application, let's try to compute the inverse Laplace transform of the function 1 over square root s times s minus 1. Now if we take fs to be 1 over square root of s and gs to be 1 over s minus 1, then we are trying to compute the Laplace inverse of fs gs multiplied by gs, and so we can use the convolution theorem. Note that the Laplace inverse of fs, this is 1 over square root of t, this is 1 over gamma half times 1 over square root of t, because the Laplace transform of 1 over square root of t is nothing but gamma half over s to the power half, which is square root of s. So similarly, this inverse Laplace transform for gs, this is quite easy, and this is simply e to the power t, and so the inverse Laplace transform of fs gs is given by the convolution of these two functions, ft and gt, where fx is 1 over gamma half 1 over square root x and gx is e to the power x. So let's try to compute what is this convolution. So you get 1 over gamma half comes out, integral 0 to t 1 over square root of u e to the power t minus u du. Now this is an easy thing to compute. So you will get 1 over gamma half e to the power t comes out, integral 0 to t 1 over square root u e to the power minus u du. So if you let v equals square root of u, which implies dv is 1 over 2 square root u du, and so v goes from 0 to square root of t now, and so you get 1 over gamma half e to the power t and 0 to square root of t, then 2 times v 2 over v, then you have an integral 0 to t e to the power minus v square dv, and there is a factor of 2 outside, 0 to square root of t. And so now we know that this is the error function for square root of t. So let's rewrite it as e to the power t 2 over, now gamma half is square root of pi. So 2 over square root of pi integral 0 to square root of t e to the power minus v square dv. And this function is nothing but error function evaluated at square root of t. So we get the inverse Laplace transform of fs times gs, which is 1 over square root s times s minus 1. This is nothing but e to the power t, error function of square root of t. Now from here you can also, now if you call this function say ht and this function say hs, then you can also compute the Laplace transform of error function of square root of t, which we computed before, but we can also check it from here. Then the Laplace transform of error function of square root of t is the Laplace transform of e to the power minus t ht, and so this is h of s plus 1 because we have a factor of e to the power minus t. So by translation theorem, first translation theorem, we have a s plus 1 here, and so this is nothing but 1 over s times square root of s plus 1. Okay, this is valid for s greater than 0. So we get the same answer for the Laplace transform for the error function of square root of t. As another application, let us show that gamma half is equal to square root of pi. We have been using this value for our computations, but let's prove this using our convolution theorem. Using the convolution theorem. So for this, let me take two functions ft. So first let me fix alpha and beta greater than 1, greater than 0, and ft I am taking t to the power alpha minus 1, and gt is t to the power beta minus 1. Now let's compute the convolution of f and g. So this is the integral 0 to t to the power alpha minus 1, t to the power beta minus 1, u to the power alpha minus 1, t minus u to the power beta minus 1 du. And here this integral now exists in general as an improper Riemann integral. This is because if alpha minus 1 or beta minus 1 is less than 0, then one of these two factors may have a vertical asymptote at 0, and so this will be an improper Riemann integral. Anyway, we can try to compute this explicitly. So let's put u equals tv, then du equals tdv, and v goes from 0 to 1. So then this integral becomes 0 to 1 t to the power alpha minus 1 v to the power alpha minus 1 t to the power beta minus 1 1 minus v to the power beta minus 1, and then you have dv times t. So you have 1 power of t here, 1 power of t here, and 1 power of t here. In total you get t to the power alpha minus 1 plus beta minus 1 plus 1. So this is nothing but alpha plus beta minus 1, and the integral you get in the end is 0 to 1 v to the power alpha minus 1 1 minus v to the power beta minus 1 dv. Now this function on the right here, this is a special function called the beta function, and it is denoted by beta b of alpha beta. Now we can try to compute the Laplace transform for the convolution of f and g. So the Laplace transform for the convolution of f and g, this is nothing but Laplace transform of t to the power alpha minus 1 multiplied by Laplace transform of t to the power beta minus 1, and these are given by gamma of alpha minus 1 plus 1 over s to the power alpha minus 1 plus 1. So this term is simply gamma alpha over s to the power alpha. Similarly, we get gamma beta over s to the power beta, and so this is gamma alpha multiplied by gamma beta over s to the power alpha plus beta, valid for s greater than 0. On the other hand, we know that f star g t, this is equal to the beta function evaluated at alpha beta multiplied by t to the power alpha plus beta minus 1. So if you take the Laplace transform on both sides, this is the Laplace transform. Now this is a constant, so this is simply beta alpha b of alpha beta. Then we have gamma of alpha plus beta over s to the power alpha plus beta, and again valid for s greater than 0. So then we have this equation b of alpha beta gamma alpha plus beta equals gamma alpha gamma beta. Because this is valid for all s greater than 0, we can simply put s equal to 1 on both sides, and so we get this equation. So this is for alpha beta greater than 0. So our beta function can be expressed in terms of the gamma function in the following formula, which is a well known formula: gamma alpha gamma beta over gamma alpha plus beta. Now to compute gamma half, so to compute gamma half, put alpha equals beta equals half. So then you get b half half is equals gamma half times gamma half over gamma 1, but gamma 1 is simply 1, so this is gamma half whole squared. On the other hand, b half half is equal to the integral from 0 to 1 u to the power minus half 1 minus u to the power minus half du. This is just from the definition of our beta function. And so if you put u equals sine square theta, then du is 2 sine theta cos theta d theta, and theta goes from 0 to pi by 2. And so if you evaluate this integral now from 0 to pi by 2, the first one is simply 1 over sine theta. I am only taking the positive part, so 1 over sine theta, and the second one will be 1 over cos theta, and then you have 2 sine theta cos theta d theta. So sine theta and cos theta terms cancel out, so this is simply 2 times pi by 2, and this is simply pi. So this implies that gamma half square equals pi, which implies gamma half equals square root of pi. So with the help of Laplace transform, we derived the formula for the beta function, and we evaluated explicitly at half half this integral. Then we get the answer gamma half equals root pi. So in this way we can use the convolution theorem in many ways, and there are many other applications, but now we will come to the crux of this course, which is to solve ordinary differential equations, linear partial differential equations, integral equations and differential equations, and so on, using all the results that we know so far, and they will give you a very powerful method to solve these kinds of equations.